graphical summary of quantitative data. For quantitative data, we can also use frequency distribution similar to qualitative data, but there is a difference. So let's see. So first, the ideal frequency distribution is the same. It lists the distinct data values x along their frequencies. But because it's quantitative data, this x, the data values are numerical. Whereas for qualitative data, which are categorical data, the data values are categories, such as colors um, or body parts in types of rehabs we saw in earlier video. But in quantitative data, in frequency distribution, the data types are numerical values. Relative frequency, similar idea. Each distinct item describes amount of times an item appears in data set, divided by the total number of observations. So similarly, it represents proportion. So if we were to do a quick table, the x are data values or numbers, and f is frequency. So if I divide by total number n, total, we get proportion. So let's look at an example. 15 members of a class were polled about number of siblings in their individual families. Construct a frequency distribution and a relative frequency distribution for their response, which are shown below. So first, we need to organize this using frequency distribution, which is the table. So there's x, and f is a frequency. So for x, I'm going to label all the numerical values: 1 sibling, 2 sibling, 3, 4, 5, 6. And we count how many are there in each data. So let me color code it. So 1, we have 1, 2, 3, 4. 4 people with 1 siblings. Let's count 2. 1, 2, 3. 3 people with 2 siblings. Let's look at 3 siblings. 1, 2, 3, 4, 5. 5. 5 people with 3 siblings. And let's look at 4. 4, there's only 1. 4. Oops, sorry. That's meant to write 1. Only 1 person with 4 siblings. And let's look at 5. There are only 5. 1 person with 5 siblings. And lastly, there's 1 person with 6 siblings. Oh, I made this error again. I'm sorry. I meant to write 1 here. 1 person with 5 siblings. 1. So this is a frequency distribution. This table is frequency distribution. Okay, for relative frequency distribution, we extend from this table. So let me copy this table. So I'll just copy the information from frequency distribution. Then this is relative frequency distribution where I'm going to do f divided by total number. So for each section, I'm going to do 4 divided by total number. There are 15 members. 15. And we can put in decimal. This is about 0.26, and it's actually repeating 6. 3 divided by 15, 0.2. 5 divided by 15, which is 0.3. Repeating. 1 over 15, 1 over 15, 1 over 15, which is 0.06 repeating, 0.06 repeating, 0.06 repeating. Oops. So this is a relative frequency distribution. which shows proportion. Relative frequency distribution. One note, when we add all the relative frequency, we should get 1. These add up to 1. So for quantitative data type or quantitative variable, we can use histogram to organize using graphs. Not bar graph, it has histogram. They look similar, but there's a key difference, which I'll explain in a second. But the bars are the same width, similar to bar graph. In histogram, again, histogram is different. This is not bar graph, different. Not a bar graph. And high represent the frequency or relative frequency, and we need to label axes. And the important distinction in histogram is bars touch. We can see in this example, this graph shows frequency and number of customers at a local Wendy's. And as you can see, the bars touch. Whereas in bar graph, bars do not touch. In histogram, bars touch. And I'll explain why. Because in histogram, because it's quantitative data, the x-axis is numerical value, not categories. Or we can think as a category of numbers, but it is a numerical measure rather than whereas the body part example we saw in earlier video about qualitative data, the body parts are category, which is why we could rearrange it, make a parallel chart in bar graph. But in histogram, we cannot just rearrange it because these are number, smallest to greatest number. So in histogram, bars touch, we cannot just rearrange it any way we want. And it has to be follow the numerical order. Okay. And it also shows gap. If you can tell, oh, this doesn't touch it, this means that there is no customer of 10. Okay. But there's a customer 5 and 6 are right next to each other, so that's why they touch. Okay. So let's do an example of graphing histogram. So this is same data from the previous example. So using the same data from previous example, I'm going to graph histogram. So let me copy the frequency table first before we draw histogram, because having a frequency table helps us graph frequency, draw histogram. So there is a frequency table from the previous, well, or using this data, and there's an x-axis. For just like for any graph, the labeling x-axis is very important. So I label number of siblings and frequency. So 1, 2, 3, 4, 5. Let me label that. And here I'm going to do 1, 2, 3, 4, 5, 6. Then we'll start drawing it. So for 1, there was 4. So I made this bar. And for 2, it touches, there are 3. So it looks like this, 3, and should be same width. So this should be same width, this and this. And 3 is 5, so here. And you may wonder, why does it be same? One could argue if it's not same, it could actually confuse the reader, right? When they're looking at, oh, is that purposely different or not? So we want to make it same width. There are 5 for the 3 siblings. 4, there's 1. So all these are 1, like this. So this is how we would manually draw a histogram. So another thing, hypothetically, let's say there's no 5. Then we should still label 5 and no bar there. That's very important for histogram. But in this case, that wasn't the case because we had a data set for all the numbers. Let's look at another example of histogram. 30 students selected randomly in the school in one morning were asked to estimate the number of hours they had spent on schoolwork in the past week, both in class and outside of class. Their responses are shown below. Create a frequency distribution and a histogram using 7 classes. I'll explain what 7 class is in a second. Here we have many data. So oftentimes it doesn't help us to just draw a histogram by using all the numbers. So what I'm saying is when we create a table, here's the data set X and frequency. And it seems here that a lot of numbers, there's so many numbers here, 4, 5, 3. So we're going to have a lot of numbers here, right? Which is fine, but it doesn't sometimes help us organize the data as we like to. So that's when the idea of classes come in. So classes are essentially, we're putting range of numbers for each data set, each range. Okay. So first, what we do when we use classes, find the largest data value. Find the largest value, which in this data, the largest data value is 42. Okay, so find that. And second step is take the largest number and divide by number of classes. So here, what we did is we're using 7. 7 is the picked by the problem. We can always manually choose. We can have 10 classes, 5 classes, depending on the data, depending on what we want to achieve. But here we're doing 7. So we're doing 42 divided by 7 is 6. So what this is saying is that we have 6 numbers in each column, each row. Okay, so instead of just putting one number here, 3, what we're doing is we start from 0 and 0 to 6. And I'm counting how many numbers do I have between 0 and 6. And similarly, I'm doing after 6 is 7, 7 to 13. So this width is 6, and this number comes from here. This is also 6. There's 6 numbers, 0, 1, 2, 3, 4, 5, 6, or 7 numbers. But the width, the length is 6. And here, 14 to 20. Keep going. 21 to 27. 28 to 34. 35 to 41. And lastly, 42 to 48. So by doing this, when we draw a histogram, the bar width will be same, all length of 6. And now what we do is we count each of them. Between 0 and 6, how many do I have? 0 and 6. So I count them, 3, 4, 5. So there are 3 data values between 0 and 6. So you can think this kind of like as a category. We're putting the range of number for each row. But we don't call it category in this context of quantitative variable. We call it classes or a class. So in this class of 0 to 6, there are 3 data sets. Then now we count between 7 and 13. 8, 10, 12, 11, 9, 7, 13, 8, 12, including 13. So there are 9. So that's to 40 to 14 to 20. There are 18, 14, 20, 16, 14, 16. Yeah, that's it. So there's 6. So repeat these for all the rest of the classes. So I'm going to do that because this is just counting process. So let me do that. You're welcome to recheck it by yourself. So this is a frequency table for this data set using 7 classes. We decide to have 1, 2, 3, 4, 5, 6, 7 different classes, and each class has same width. Okay, so let's draw a histogram using this information. Let me come down here. You can always label your axes. So this is number of hours schoolwork. This is frequency in terms of how many, right? So let me label the axes. So all the axes are labeled to class 0 to 6, 7 to 13. And then we just draw a bar graph. 0 to 6. Oh, I forgot to label this part. 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 to 6 there are 3. So there's a bar. 7 to 13 there are 9. So all the way here. 14 to 20 there are 6. Same for this 6. 28 to 34 there's 3. 35 to 41. 42 to 48. Oops, sorry, that was wrong. 35 to 41 is 2, not 3. So it should be lower. And 42 to 48, 1. So something like this. So it's a histogram of this data using 7 classes. If we don't use classes here, we're just going to have a lot of short bars, because a lot of numbers actually appear only 1 or 2 times. So we're going to have a bar for 3, 4, 5, 6, 7, 8, 9. We just have long histogram. Again, which is not wrong, but it doesn't capture the data in a summarized way. We also don't have too few of number of classes either, because then we're going to have a lot of data clustered in classes, 2 or 3 classes. Okay. Another way we can organize data for quantitative data is using stem and leaf display. So let me just do an example to show you how stem and leaf works. So here, all the numbers, not all, but most of the numbers are 2 digits, right? So what I do is I make a stem. You can think like this. Here's a vertical line. And I have 0 means 0 for, we can think as 8 as 08 or 0903. And for 1, 2, these are 10s, 20s, 30s, 40s, and there's no 50s. So we're putting all the numbers smaller than 10 in the first row. So let me mark it. We don't want to miss any of them. So for example, 3, 4, 5, 7, 8, another 8, and 9. Okay, so, and we must write in order. So 3, 4, 5, 7, 8. If it's twice, we need to write it twice. 8, 9. Okay, so that's all the numbers less than 10. Now for tens, think this as 10. So that we only put the second digit. So let's mark all the numbers first. So I have 10, 11, 12, 13, 14, another 12, 14, 16, 16, 18. Yeah, that's all the numbers in tens. So here I'm only putting the second digit. So this means 10, 11, 12, 12, there's 2 12s, 13, there's 2 14s, 4, 4, 2 16s, and 8. So that's what it means. Instead of writing all numbers, we're writing tens are like these. These are numbers in tens. Let's do 20s. They're 20, 24, 25, 26, 22, 27, 24. Again, we must write in order, smallest to greatest. So I have 20, 22, 24, 24, 25, 26, 27. So let's look at 30s. 30s, I have 31, 33, or 31 again, 35. That's it. So I write 31, 31, 33, 35. And 40s, I have 40 and 42. So 40 and 4. Oh, let me write the same color. 0 and 2. And in order to help the reader, we often do this. We can get a note or to just show them how to read this. For example, 2 means 22. So this is called stem and leaf plot. Stem and leaf plot has many benefits. First, it can easily tell us the smallest and greatest value, or an outlier if we have an outlier. Also, it shows how many of them repeated. Here we can tell there's 2 8s, 2 14s, 2 24s, 2 31s. So this is how we organize stem and leaf plot. Again, for stem and leaf plot, if it repeats, we have to write it twice. It also shows that, okay, we have the ones the most. Lastly, just quick point. I've been emphasizing x-axis and y-axis a lot. Especially for y-axis, we need to be careful when we read a graph, and especially when we construct a graph. Let's look at these two graphs. Let's say this is asking a question about the public about do you support or oppose a new policy, new local government policy, right? And seems like the one on the right has more opposed, like looking at the bar lengths, almost 3 times more opposed. Whereas the left side, support and oppose, looks close, at least closer than the right side. Let's look at this as A and B. But actually, if you look at the numerical value, the oppose is about 55 on the B, and support is about a little below 45. But same here, near below 45, and oppose is also 50. So the graph B is actually misleading because they only label the x-axis from 40 to 60. So we always have to be careful when we read the graph. Are the x and y axis manipulated in any way to manipulate the data? Are they changing on purpose to give an impression that there is more oppose than support? Whereas numerically, if you look at all the y-axis, they're pretty similar. So that's something we always should be keep in mind as a consumer, just as a person when we look at a graph or any data in that aspect.